Today what we're going to be doing is solving the question, how much work did Sisyphus do on his way up the hill every day for eternity? As we can see, we've got little Sisyphus here pushing his very heavy boulder. At some point, the boulder is going to come back down this very steep hill. Once it does come back down the hill, the question we are then going to answer is how fast is it going when it reaches the bottom? Finally, we're going to say, if it were to collide with somebody, how much momentum would it impart? So let's make some assumptions here. Let's assume, first of all, that we've got a rectangular block here and a very steep incline. This is just going to make poor Sisyphus's work multiply by a lot if the boulder can't roll and if the incline is super steep. We're also going to assume a coefficient of kinetic friction of about 0.7. We're finally going to assume that the distance that he pushed it before it started rolling back down was about 1,000 meters. Now, what we're going to want to see is how much force he had to apply to get it going at that constant velocity. So in order to do this, first we've got our diagram here. Next, what we're going to do is draw a free body diagram. So a diagram that's free of any of these markings, besides just the arrows of the vectors of force. So here we've got his force applied goes up the hill. Now there are going to be a couple forces going down the hill. Number one is going to be an element of gravity, which we can call Fg parallel. Number two is going to be a frictional force. Now that is going to depend on the normal force, which is always going to be perpendicular to the surface. It's going to point up like that. And it's also going to depend on mg, which is the gravitational force, but that's always going to point just straight down from the block towards the center of the Earth. Now we're just going to gather all of these forces together. And of course what that's going to be called is F net. That's just the gathering of all forces, or the summation of all forces. In our case, what we're going to have is F applied is the force that Sisyphus is applying on his way up. Working against that is going to be that gravitational force that's parallel to the surface, also that frictional force. Now how do we account for those two? Well, the gravitational force that's parallel to the surface is fairly simply displayed as mg sine theta. Luckily we have all those values, so we can work that out right now as 9,800 times 0.94, and that's going to be 9212 newtons. So that's how much force gravity is using to pull that rock back down. In addition to that, Sisyphus has to fight against friction. Friction is going to be equal to mu k, the coefficient of kinetic friction, times the normal force. In our case, that's going to be mu k times mg cosine theta, since it's pointing perpendicular to the surface. When we multiply that out, what we're going to find that is equal to is 2352 newtons. So we have F net equal to F applied minus 9212 minus, again, because they're both working against F applied, 2352. That's going to be equal to the mass of the boulder times the acceleration of the boulder. Now another assumption we're going to be making is that the velocity is slow but steady. In other words, constant. So that's going to mean that our acceleration is equal to 0 meters per second squared. That means that in the above equation, it's going to simplify down to F applied minus 9212 minus 2352 is going to be equal to 0 overall. That's going to mean that the F applied is equal to 9212 plus 2352, which is going to be 11,558.26 newtons. Wow. Now let's do another part of the problem. Let's say that Sisyphus has made it all the way up this gigantic hill with his gigantic boulder, and now, as we see in the video and as we know from the myth, it just starts rolling back down. How much work is that boulder going to do if it rolls, say, 1,000 meters? Well, what we have is we're going to have F net is going to change a little bit, because in this case, if we draw our free body diagram, we're going to see that we're going to have mg sine theta pointing down the hill, just like before, but this time friction is going to be pointing in the other direction. So what we're going to wind up with is F net is equal to mg sine theta. This time we're going to subtract off mu k times mg cosine theta. This is because friction always acts against the motion of the particle. In this case, that's going to be 9212 minus 2352. So that's going to mean that our F net in the end here is going to be 6860. Now, just out of curiosity, we can find out how fast it's accelerating. It's not going to be 9.8 meters per second squared because it's encountering friction and because it's on an incline. So let's see how fast it's accelerating. 6860 newtons is going to be equal to ma. So that's going to mean that our A is going to be equal to 6860 over 1,000. That's going to be 6.86 meters per second squared down that hill. So it's a pretty good acceleration, but not quite as fast as it would be in a vacuum falling. So let's find out how much work that boulder does on its way down. Work, as we know, is just FD cosine of phi. This phi is the angle between F and D. In our case, since the boulder is falling down the hill and the distance is also being measured down the hill, phi is going to be 0. So that's going to mean that cosine of phi is 1, and work can simplify to just F times D. In our case then, work is going to be 6860 times 1,000. It's going to be 6.86 times 10 to the 6 Newton meters, which is equal to 6.86 times 10 to the 6 joules. Now, what else do we know about work? Well, we know through the work energy theorem that work is equal to the change in kinetic energy. So that's going to be equal to 1/2 mvf squared minus 1/2 mvi squared. In our case, we're going to take I to be equal to 0 because the boulder begins to roll from rest. So in our particular case, we're going to have 6.86 times 10 to the 6 joules is equal to 1/2 of 1,000 kilograms times Vf squared. So final velocity then is going to be equal to 117.13 meters per second. Okay, now we're going to use the conservation of momentum to find out how fast the boulder is going after it collides with a person who weighs 70 kilograms. So we're going to say m1v1 plus m2v2 initial is equal to m1v1 plus m2v2 final. If we simplify this out, saying the person is initially at rest, so that's going to be 0, we're going to say that 117,132.4 is going to be equal to 1070 times that new final velocity. So the final velocity will be equal to 109.47 meters per second.